This is the 42nd lecture of the course MTH 204A for section B. Recall that in the last lecture we started discussing about free abelian groups. So what is a free abelian group? It is an abelian group having a basis. So the meaning of basis is exactly similar to that of the basis in vector space, that every element in the group can be written as a unique integral combination of unique finite integral combination of the basis elements. Okay. And if an abelian group admits a basis which is finite, then we call it a finitely generated abelian group. Examples we have already seen. Zn. So for any n, this is a finitely generated abelian group, and in fact after isomorphism we can immediately see that any finitely generated abelian group has to be isomorphic to Zn. So like let G be a finitely generated free abelian group, finitely generated free abelian group. Let S, so by finitely generated it means it has a basis having n elements. So a priori we do not know whether it has whether it can have though it has one finite basis, whether it can have an infinite basis or not. Also we do not know that it can whether it can have any finite basis whose number of elements is different from that of the basis which that of the basis which we have considered. So that those things we know, but of course in due course of time we will rule out such possibilities. So let this be a basis of G. Okay. Then since this is a basis, it's quite easy to see that so this is the each of these x, so each of the summand is the cyclic subgroup generated by the ith basis element. So thus we have several cyclic groups and all these groups are of course isomorphic to Z, because like once a group is a free abelian group, we have proved that it cannot have any element of finite order. So there actually all these xi's are isomorphic to Z. Hence this whatever we have written is actually isomorphic to n copies of Z. Okay, is n copies of Z. Now since G is a basis, x1 of xn is a basis of G, so it is easy to see that this will be equal to G. Why? Because every element of G, since x1 of xn is a basis, so it can be written as a sum of elements from these subgroups, and so furthermore to show the uniqueness, so let me again remind you what is the meaning of this. Whenever we write that a group is an abelian group is direct sum, so I think I should remind you that suppose G is an abelian group and it is the direct sum. When we write this, it means that this map, the natural map sending so this abelian group, we write it in additive notation. This is an isomorphism. Okay. Equivalent way to put that is every G in G can be written uniquely as G1 up to Gn, where each Gi from capital Gi. So like these things we have proved the equivalence earlier, so I have just reminded you. Now in view of this, since this is a basis, this is clear, and so in view of this, this is clear. So Yeah, so thus we have proved that if G is a finitely generated abelian group, then G must be isomorphic to some z to the power n. However, as I said, there are still possibilities where G can have another basis consisting of precisely m elements where m is not equal to n. So these possibilities are still there till now. We haven't ruled them out, we have to rule them out, and of course G might have a basis of consisting of infinite elements. That possibility has also not been ruled out yet. So we are going to rule out such things right now. So yeah, so this thing is clear that all finitely generated abelian groups are actually obtained in this way up to isomorphism. Now let us come to the main thing that I am talking about for some time, that if it has a basis consisting of I mean in a single sentence, what I want to prove is two bases will have same cardinality, and in order to make these situations simple, and of course that will be enough for our purpose, we will work with finitely generated abelian groups only. When things are not finitely generated, you might need some further set theoretic stuff, namely some transfinite kind of argument, but I don't want to get into that. So from now onwards, most unless otherwise stated, all the abelian free abelian groups, or in fact the abelian groups that I am going to deal with, will be finitely generated. Okay. So what I want to prove is that let me build things up one by one. So let G be is a free abelian group, is a finitely generated free abelian group, finitely generated free abelian group. I think sometimes customarily for abelian things we use these letters. A finitely generated free abelian group, and let x1 up to xn a basis of A, as we have observed that from A to this group we have an isomorphism, right, because from the basis, from the fact that it is a basis, we have this direct A is the direct sum of the subgroups. That is exactly same as saying that we have a very natural isomorphism here. So what let me denote that by F. So what is that isomorphism? If I want to write that explicitly, take any element x from A, x will admit such an expression in kxk. So I think maybe I should use k. Then we send it to this tuple in kxk. Okay. Now what I do is so I would like to run some induction argument, okay, on the number of basis elements. So whatever I am going to do will be clear in a moment. So what I am doing right now is I am just projecting. So with this I consider the projection map. Okay. So whenever we have a direct sum decomposition, then that is automatically yields several projection maps onto the summands. So let me denote now the projection map by F. So basically maybe I should first write it as G, and F is basically the composition of G and F, G and pi. Is n1 x1. Okay. So this is actually therefore a map from A to. So this is a map from A to the cyclic subgroup generated by X. So now what we do is we consider the restriction of F F restricted to, okay. So let us take a subgroup, let B be a subgroup. So what are the things that are given to you? A finitely generated abelian group, we have chosen this to be a basis of A, and from the basis we have such an isomorphism. So I can compose the isomorphism with that projection. This is what I am defining as F. Now let B be a subgroup of A. So it makes sense to talk about the restriction of F on this. Okay. Well, one thing is clear, that the F used to be surjective, but once I restrict that to B, that this need not be surjective. However, the image, so one thing is clear, that this restriction, so the image of B is a, so this is isomorphic to Z. So image is is either trivial or it is some infinite cyclic subgroup of Z. Okay. So image is either trivial or some C. C is a non-trivial infinite, or some C. So basically I think together we can put this, let this be C, where C is a cyclic subgroup. In fact, every subgroup of this will be cyclic. C is a cyclic subgroup of this. So remember that either C is trivial or it is infinite cyclic group. Okay. So the whole point is that in the later case, so certainly C is going to be a free abelian group, being an infinite cyclic group. Okay. So we will use that. So where are we now? We are now at okay. So what we are considering, we are working with this map. One thing is clear, that if we look at first F, the way F is defined, so the subgroup generated by x2 up to xn lies in the kernel of F, right? Lies in the kernel of F. Sorry. So that is the opposite one. So the kernel is precisely this group for F. Okay, it's precisely so. And next, what we next see is let B1 be the kernel of the restriction. Okay, B1 be the kernel of the restriction. Then certainly, so the restriction of the kernel and original kernel is this. So therefore, B1 has to be contained inside this subgroup, right? Because the kernel of the restriction will be contained in the kernel of F, and kernel of F is precisely this. So therefore, B1 is a subgroup of a finite group of a finitely generated free abelian group, which is generated by, I think I should change the notation somewhere, this will be K. So the point is that B1 is a subgroup of a finitely generated free abelian group, which a finitely generated free abelian group consisting of a basis whose number of elements is k minus 1. Okay, that's what we have obtained. The B is the subgroup of a finitely generated free abelian group having a basis consisting of exactly k minus 1 elements. So you see that the scenario is now changed. Like earlier, B was a subgroup of a finitely generated free abelian group which having a basis of exactly k elements. From that, we have generated a group B1, which is the subgroup of a finitely generated free abelian group having basis, k minus, having basis consisting of precisely k minus 1. So we can run an induction. Now by induction, so by induction, okay, so I think let me write down the statement formally here. So the thing is, because almost we are done. Statement is like, let me write down the statement here. So basically, I mean, I am giving the argument for the proof. So let this be a finitely generated free abelian group, and is a finitely generated free abelian group. So this is the actual statement, and let it be a subgroup of A. Then B is also finitely generated. Okay. I mean, I haven't completed the statement yet, because this statement has further that contains further conclusions. I will do them, I will write them one by one. So hereby, so right now just let me stop, let me stop with this and come back here. So by induction argument we see B is finitely generated, B is finitely generated and free. Yeah, B is also B is a finitely generated. B is also finitely generated and more importantly free. B is also a finitely generated free abelian group. As I said, we will see much more. So therefore, by the virtue of by this induction principle, we conclude that V is also finitely generated free abelian group. This B1. Now we appeal to a lemma, appeal to a proposition proved last time. So that yields that there exists a subgroup C1 of B such that this whole B, B is this kernel B1 direct sum C1, and the restriction of the further restriction of, I mean, we have already restricted F to B and C1 is a subgroup of B. So if we further restrict the F C1, then that is going to be an isomorphism from C1 to the subgroup C. Okay. This is what the situation. Now what are the possibilities for C1? If C is trivial, if C is okay, I think here we have to be slightly careful. I think the division of the case is to be done before we come to this. Yeah, I will just modify. So here, let me do it in this way. So B1 is a finitely generated free abelian group. Now consider two cases. If C is trivial, then what does that mean? So this whole map is trivial. So then B1 will be whole of B. Therefore, like B1, therefore B itself will be finitely generated free abelian group. So in this case, by induction we obtain that B is also a finitely generated free abelian group. Now if C1 is non-trivial, if C is non-trivial, then basically it is a map from B to a free abelian group. It is a surjective map from this F restricted to B. B is a map from B to a subject onto homomorphism from B to a free abelian group, because any infinite cyclic group is a free abelian group. Hence by the previous proposition we will obtain a C1 such that this happens. Okay. Now once it is there, so the rest so this is a free abelian group. So, therefore, like let Z be a generator of C1 and let Y1 up to Ym is a basis of B1, then it is, you can immediately see the way it is there from the direct sum decomposition, it is now clear that is a basis of B. Okay. So, thus by induction we have proved that for any finitely generated free abelian group, its any subgroup will also be finitely generated, subgroup also be finitely generated and free. So, what was the argument? Argument was very simple, that we consider this projection and then restrict that. So, now we have exactly two cases. If this is trivial, so as we see that after projection, once we see the kernel becomes a finitely generated free abelian group. Now we have two cases. So, this is this is what we got by induction. Now, if C is trivial, then this will be equal to B. So, thus B will be a finitely generated free abelian group. If this is not trivial, so if this is not trivial, then we use a previous proposition proved in the previous class that shows that it has such a decomposition, then it is actually trivial to see that this is going to be a basis for B. Okay. So, this immediately follows from this direct sum decomposition. Okay. As I said, we can further deduce that, I mean, not only B is finitely generated. So, for example, what do we expect? What have we seen in case of vector spaces? If a vector space has dimension n, then any subspace will also be finite dimensional, and not only that, it will have a basis. So, its dimension will be less or equal to that of the main space. So, similar thing you should also expect here. So, for that we have to formulate according to this. So, A is a finitely generated free abelian group, and assume that A has a basis consisting of k elements, then not only okay, so we assume this, then let we have subgroup of A, then B is also finitely generated, a free abelian group, and B has a basis having at most k elements, having at most okay. So, in order to prove the part which we have just joined, so that also follows like in the original proof which I have talked about. So, like when we run the induction argument, so from the induction argument, so this is, suppose this is the whole statement we are going to prove by induction, including this number of elements in the basis. So, if we, so like the same proof, I mean there is no change, but we will just add appropriate things. So, when we run induction, we can assume that we obtain that by induction B is a finitely generated abelian group and has a basis of at most k minus 1 elements. No, because this is subgroup of a finitely generated free abelian group having generated by k minus 1, having a basis of k minus 1 elements. So, by induction argument, when we say that B1 is a finitely generated abelian group, we can also further say that it has a basis of having k minus 1 elements. Then of course, the rest of the argument also holds, and then therefore, this basis will have at most k elements. Okay. That proves the theorem. All right. So, I hope that this extension of the argument is quite clear to you. Earlier we just focused on the finitely generated business, but now I am saying that now you can see that the same induction argument also, so I mean same induction argument also take care of, I mean it can also take care of this number of elements in a basis, that part as well. So, if this is our full statement, that is B, conclusion is B is also finitely generated and having a basis less or equal having at most k elements. So, if these are full statements, so starting from this B, we arrive at B1, which is a subgroup of a finitely generated free abelian group with a basis of at most k minus 1 elements. Okay. Then according to induction, this also becomes a finitely generated free abelian group with this much, and the rest take care of, and then the rest part is take care of yeah. And once we have this, then from this decomposition, I mean not only we get the finitely generated free abelian group, this B, also the number of elements, that part is also taken care of. All right. The next thing is you must have noticed that throughout I am talking, I am speaking in the language, throughout I am using the sentence that using the phrase that having a basis of this many elements. So, I have to use that because right now, so because till now I haven't established that like if there is a basis of n elements, then every basis will have n elements. If something like that we can establish, then we can simply denote that number by something. In fact, that is what we are going to do, we will call it a rank. Then we can simply say that if A has rank k, then any subgroup will be also be free with rank less or equal to k. Okay? But that I cannot say because so far I haven't proved that any two bases will have same number of elements when the group is when the A is finitely generated abelian group. So now I am going to prove that. In fact, unlike that of vector spaces, here we prove it first. That is what you can see. We prove it first with all. I mean, what I mean by this is what we prove first, where we have to use this phrase. Now, using this, we will prove that any two bases will have some number of elements. So, try to see the difference. In case of vector space, we did not, there the scenario was different. We somehow invoke the results from system of linear equations, and then that settles everything. That settles, but certainly something like that does not work here. So, here the line of argument is something different. Here we first prove this. So, even till this point, these possibilities are there that there could be a basis having different number of elements. That possibility is there. But now, using what we have proved, we are going to rule out that case. I hope you are able to see the difference. So, let me also put it here. Put it here. Furthermore, any two bases. Any two bases. So I should put it in this way. So, any basis of B must be finite. So, like that, and number of elements in a basis is unique. This is the part this part I will prove now. So, the again argument is somewhat subtle. So, let S be a basis of B having m elements and T be another basis. Right now I am not saying whether T is finite or infinite, T be another basis. Okay. T be another basis. So, now try to observe see that since B is having a basis of exactly m elements. So, B has to be isomorphic to direct sum of m number of Z. Okay. Now, therefore, it is clear that B modulo PB. So, where fix a prime P, you can take 2, I do not mind. PB is the subgroup Px, x belongs to B. This will be a subgroup. The main point is that B modulo PB, of course, isomorphic to. So, this is quite clear. This will be Z modulo PZ, Z modulo PZ, n number of copies. Okay. So, B modulo PB will be having p to the power. So, the order of B modulo PB will be p to the power m. Okay. Now, let T be another basis. So, suppose that T consists of, T contains at least R elements where R is less or equal to n. So, that means T is, so let those R elements be x1 up to x1 up to, maybe I should change the notation a bit, z1 up to, or maybe t1 up to tr, and then whatever is rest, let us put that by t dash. Okay. All right. So, if this is the case, then it follows immediately that B is basically the direct sum of TR and of course, the subgroup generated by this subset T prime. Okay. Because since this is a basis, so every element of T can be as unit finite combination of T1 up to TR and elements from T prime, but all but finitely many coefficients will be 0. So, therefore, that shows that it will so it will be uniquely, it can be uniquely written as a sum of elements from this subgroups and this. Okay. That is, this part is pretty obvious, because when you write T as a combination of these basis elements, so the coefficients and some of the coefficients of T1 up to Tr might be 0, okay, and then then there might be a combination of elements from T prime, there the coefficients might not be non-zero. So, it's break the sum into two parts. In the first part, we have terms we have terms containing T1 up to Tr only, and there will be the rest. So, the rest part belongs here, and the first and that part belongs here. So, this is obvious. Now, then furthermore, we do the same. B modulo PB is again, so all these are in infinite elements of with infinite order. So this is and these are isomorphic to Z, right? These are isomorphic to Z. So maybe I should directly write it here. R copies plus let me keep it as usual. So then it becomes entirely clear that this will be Z modulo Pz, Z modulo Pz, R copies and then something happens to this, and okay, it is exactly same as saying that if we multiply each and every element of T prime by P and then generated by that, this same this part whatever is something I simply do not care, let me therefore put something by star. So this shows that the number of elements in B modulo Pb is at least p to the power r, right, is at least p to the power r. So therefore what do you obtain comparing these two, because like from these two it follows that r less or equal to m. So what we have observed is if T contains some r elements, there could be more, then r cannot exceed m, right. If you are able to find r distinct elements in T, whatever r be the natural number, but that then we see it cannot exceed m. So therefore this all total force says that T cannot have more than r elements, more than m elements. Okay. So thus what we have observed is the following, that if we start with a basis having m number of elements, then so what does this to say? So since B is having a basis of m number of elements, then we see that every basis must be finite. Okay. So therefore right now one thing is clear, that any two bases will, I mean if we take any basis, that will be finite, right. And this argument also shows that, like if we are given two bases, one is having m elements, another one is having let us say r number of elements, then r cannot exceed m, right. This is what we have seen, that we first treat an arbitrary basis having m elements, and then this argument also show, as I said, that as a byproduct of this argument we see that if we start with another arbitrary basis with r elements, then this r cannot exceed m. Now you can switch the role of these two bases, that will give you the other inequality, that is m less or equal to r. Therefore thus you obtain any two bases will have same number of elements. Let me quickly repeat this argument, then I will move ahead. So this what does this argument show? We started with an arbitrary basis with m elements, then we see that if we take some other basis which contains at least r elements, then r must be less or equal to m. That forces, if you take any other basis, that also have to be finite, right. This is one thing. Furthermore, we have also seen that like this S and T both are arbitrary bases, right. So if we start with an arbitrary basis of having m elements, another arbitrary basis, now it is settled that this second basis, the other basis has to be finite. So like therefore we are not going now onwards, we are not going to talk about basis with infinite elements. So like once this thing is settled, so now the situation is that if we start with a basis of having m elements and another basis arbitrary having r elements, then r has to be less or equal to m, right. So this holds, this is what we see for any two arbitrary basis, right. So we can immediately switch their roles, so that gives us the other inequality, namely m is less or equal to r. That's so earlier we got r is less or equal to m, and then we see m is less or equal to r, so therefore we got r equal to m. That shows any two bases will have some number of elements. Okay. Let again understand, our argument is actually having two phases. In the first phase, so we started with an arbitrary basis having m number of elements, we started with that, then we proved that if we take another basis that cannot be infinite, okay, and that cannot be infinite, and furthermore that can contain at most m number of elements. So this is the story of the first phase, and the story and as an extension of this in the second phase, what we observed is, if we start with an arbitrary basis having m number of elements and another basis having r number of elements, then the argument in the first phase assures that r has to be less or equal to m, but since these two bases are arbitrary, we can reverse their roles. That produces the other inequality, namely m is less or equal to r, therefore we obtain r equal to m. This shows, so m number of elements. So now by reversing the role, by role reversal, so now by role reversal, we obtain cardinality of S and cardinality of T are same. This finishes the proof. Okay. So this is for any B, and of course taking B equal to whole of A, that also proves that any two bases in A will have same number of elements. Okay. So at this point, one thing you can say that if we don't get into B, if we just work with A, then at least this part, that is what we have written here and here, this part goes through without getting into B. So therefore, therefore if we don't bother about B and just only concentrate upon the finitely generated abelian group A, then this argument also shows that this argument in fact shows that if A is the finitely generated free abelian group A, in that finitely generated free abelian group A, any two bases, if in a finitely generated free abelian group A, every basis has to be of finite cardinality, and the cardinality of any two bases will be same. Okay. So the point again, let me repeat that if we just instead of bothering about B, if we just stick to this and this, whatever we have done here and here with A, then this argument at least assures that like no basis in A can have infinitely many elements, and furthermore any two bases in A will have same number of elements. So that is without getting into B. Of course you can prove that the number of elements in basis A is unique. There is no problem in that, but however what we have proved is actually somewhat I would say stronger, that yeah. So what we have proved is kind of put in a much more stronger or elegant way. It says that if we take any B, then B will be finitely generated, and any two bases in B will also be. So like as I said, it's put in a different way that apparently looks stronger. Anyway, but of course actually that need not be the case. Like another way of putting that is the following, that you do this uniqueness in the number of elements of a basis first. So that will show that will be entirely concerned with A. Now furthermore you can prove that this B will be finitely generated, and B will be free and finitely generated. Okay. And then you apply the result that we have proved for arbitrary A for B. Okay. That will also give you the uniqueness of number of elements in B. So that could be another way of arguing, but if you prefer that, you can also do that. Basically just somewhat the this is just the ordering of the argument which you put first, which you do second, but ultimately you are getting the same thing. Right? So this is what how we have presented the argument. I also told you, I mean, another way of, I mean, of course not different, just a reordering of the entire argument, that also that you can, I mean, you can also do in that way, and there you neither lose or gain anything. Okay, enough of this. So, like now we are in a position, as I said, that once the number of this uniqueness is established, we are in a position to call it something. So, this in a finitely generated abelian group, the number of elements in any basis, which is of course unique in view of this, is called the rank of the abelian group. Okay. So, thus in this in this new terminology, you can simply restate this theorem, I mean rephrase this theorem as follows, that if A is a finitely generated free abelian group with rank k, then any subgroup of that will also be finitely generated and having rank at most k. Okay. So, the point is, you see that this the scenario is almost quite similar to that of vector spaces, namely finite dimensional vector spaces. Okay. So, now let me move further. As I said, my aim is to prove the structure theorem. For finitely generated abelian groups, we have already proved for finite abelian groups. So, one thing is clear, that a finite abelian group is okay. I will do that. Let me go step by step. So, like let A be an abelian group. Okay. A in A is said to be a torsion element. Torsion element. If it has finite order, okay. So, finite order. Now, A tor consists of all elements in A. A is a torsion element. Okay. Torsion element, this is going to be a subgroup of A. It is called the torsion subgroup of A. If this is trivial, then we call the group is torsion free. So, if this is trivial, we call A is torsion free. And the very opposite one, if A tor is whole of A, we call it A is a torsion group. A is a torsion group. Observation, of finitely generated torsion groups are indeed finite. So, when do we say finitely generated? So, in this lecture, in the last lecture, we used that word finitely generated for free abelian groups only, but the notion of finitely generated, that maybe in one of the first few classes, we have already defined this for any general group. So, if a group has a finite generating set, then we will call it a finitely generated. Okay, finite generating set, we will call it a finitely generated. And okay, so observation, finitely generated torsion groups are finite. So, this you can take as an exercise, very easy to see, because if this is a set of generators, since all of these have n finite order, so therefore, in this manner, where okay, I should m1 up to mn, in this manner you are only going to get finitely many elements, because if you look at this part, this will be keep repeating. So, mi's are integers. So, this part will keep repeating, that each of the summands, once you vary the coefficients, they will keep repeating. So thus we will get finitely many elements. So this is just like the crux of the argument I have told you. The rest you can take it as an exercise. Okay. All right. Yeah. Now let me come to the main observation. I should again put it as a proposition. So let A be a, so A, suppose A is a finitely generated torsion free abelian group then A is free. So look, earlier we proved that if A is a free abelian group then it has to be torsion free. Now what about the converse? If A is torsion free, can we say A is a free? We are proving the converse when A is finitely generated. Okay. So let me again remind you, by finitely generated I mean there is a finite generating set. Here I am not assuming A is free or anything. In fact, that is what we are going to prove. Now the confusion might arise that this earlier we used the word finitely generated in the for general groups, but in the last two lectures we have only used the word finitely generated for only for free abelian groups. So of course it it requires to convince ourselves that this for free abelian groups these two conditions are same, that is having a finite basis and having a finite generating set. Because for free abelian group we said finitely generated if it admits a finite basis. So of course it requires to convince ourselves that for free abelian groups these two notions they are not different. So I leave that part to you, that for a free abelian group it has a finite generating set if and only if it has a finite basis. One way is obvious. The second way you just have to do some work, but that's again a routine task. So let me, maybe I can put it as an exercise here as well. But as I said that in order to go with free abelian groups we can simply assume that it is a finite basis. Whenever we want, we can simply assume it is a finite basis. So exercise, if A is a free abelian group, then the following are equivalent. So this follows from what we have done. A has a finite basis, if A has a finite basis and A has a finite generating set, but please do not jump into the conclusion that every generating set can be reduced to a basis like that of vector space. Certainly that is not true, because for Z this 2, 3 is a generating set, but neither singleton 2 nor singleton 3 is a basis. So this is not like that of vector space. We have to do some work, but however this is quite routine, hence I am leaving that to you as an exercise. If you need we can, though I do not think that requires any further discussion, but if you need we can do that in discussion hour. Now let me come to this. So this is a finitely generated torsion free abelian group. We are supposed to prove this is free. Okay. So yeah. So what we do that, so it's a finitely generated group. So let S be a generating set. S be a generating set. Generating set. Let S be a generating set of A. Okay. So S is a finite set, a finite generating set. Let choose x1 up to xm to be the maximal. Choose this to be the maximal maximal is in terms of containment maximal subset S with the property with the following property. Okay, what is that property? The property is whenever this is 0 with each ni integer, then that will follow, it will imply each ni will be 0. Okay. So, this is to be interpreted some kind of integral independence. So, like we are considering all those subsets of x such that the property such that it has that property that whenever a combination vanishes, then each and every coefficient has to vanish, and like since we are working with only finitely many elements, so indeed we can choose a maximal subset with this property. Okay. So, the next step is very simple, that if this is whole of x, so I will be, this part I will be somewhat going, I will be quite fast. If this is whole of x, if this turns out to be whole of x, then certainly, well, let me do it in this way, that let B be the subgroup generated by x1 up to xm. Okay. Now, this property assures that it follows that this x1 up to xm is a basis of B. Why? That is quite clear. Since it is generated by these elements, every element of B can be written as a combination of them. That part is there by definition. Now, in order to show the uniqueness, so like that also is a very usual argument, n1 x1 up to n mxm, if that can be written as a different way. So, this is a usual argument, I would say. Then you bring everything one side and use this property, that will force each ni equal to be ni dash. Okay. So, this part is clear. Now, if this is whole of x, then since S is a generating set of A, one obtains that B is A, and that shows A is free because B has, this is a basis of B, then we are done. If not, then let y be S minus m. Okay. So, therefore, then we consider this set xm times y. So, this is also a subset of y that properly contains this. Therefore, this cannot have this property, hence there exist integers n n1 up to nm such that not all 0 and the combination vanishes. Okay. Now, I mean not all 0, right. So, you say there is at least one of them should be non-zero. There could be 0 there could be 0 also in this list. So, the question is, can n be 0? If n is 0, then we will have this, that will force all other ni's to be 0. So, therefore, n 0 means all ni's will be 0, that is not allowed to happen. Therefore, n not equal to 0, and that shows. So, n is a positive, that shows that yeah, ny belongs to this B. Okay. if necessary replacing n by minus n, we can take n to be a positive integer as well. So what we have obtained is, if this is not whole of S, then for every y in S other than this, for every y I have a n such that, so let me write it here. So this the proof is almost there. For every y in S, there exists a positive integer n such that n y in B. This is what we have observed, right? So remember, if we consider x1 up to xm, then for that n can be taken 1 as well, because they are already inside B. So therefore this statement we can further modify simply by saying this, right? Because like if it is not from x1 up to xn, of course we have n, and when it is x1 up to xn, trivially n equal to 1 works. So this is what we have. And then like here the thing is, this n depends upon y. Now like we have only finitely many such y's, so therefore taking a sufficiently large n, we can simply like switch the order of the quantifier. So we can simply say that there exists capital N in n such that for every y in S, n y belong to B, that belongs to B, right? Because you can take LCM or something, because only finitely many such small n's. And then this any element of A is a finite combination of this y, is a combination of this y's, right? Because S is generating set. So if ny lies in B, then any n times any combination of y's will also lie in B, and any time these combinations of y's are precisely all elements of B. So therefore that we obtain is, for every x in A, one has nx, n times x lying in B. Okay. Now the rest part of this argument is almost done. So from A to B, we have a map sending each x to nx, right? This map cannot have, the kernel has to be trivial, right? Because A is torsion free. Nx is equals to 0 means x will be a torsion element. So it's torsion. So this will have a non-zero x. If for a non-zero x we get nx equals to 0, then x will be a torsion element. So this map is injective. This is 1 1. So therefore thus A is isomorphic to subgroup, some subgroup of B. By definition B is free. Now by this theorem, being a subgroup of a finitely generated, B is a finitely generated free abelian group, being a subgroup isomorphic to a subgroup of a finitely generated free abelian group, A will also be free. Okay. So thus whenever we are dealing with a finitely generated torsion free abelian group, has to be free. Now that this observation leads us to the structure theorem for finitely generated abelian groups. So what we do here is, so the structure theorem, let A be a finitely generated abelian group Then the first observation is, I will prove part by part, then A tod has to be finite, is finite. Remember that like earlier we proved for a finitely generated free abelian group, any subgroup will also be free and finitely generated, but here we have not assumed A to be free. So right now you cannot even say this is finitely generated. But if we can prove it's a finitely generated, then by your previous observation that finitely generated torsion groups are being finite. So just from this we cannot even, I mean, so far we don't know whether we can say that a tod is finitely generated or not. If we can show that a tod is finitely generated, of course that will be finite. So in order to show this is finite, we will prove a tod is finitely generated. So how to do that? That's actually quite simple. That let me write down the argument here. Let this be a basis, or let this be a generating set of A. Okay, then certainly we construct this direct sum of subgroups, and from this we have a very natural map M1 x1 Mn xn that goes to summation mi xi. Okay. Remember, if this would be a basis of A, then certainly this map would be an isomorphism, but in general we cannot say because it is just a generating set. But this homomorphism is already there, this is there. I mean, whenever it is a generating set, we have this as a surjective homomorphism. So thing is that if it would be a basis, then we could have said that this is an isomorphism, but from the fact that it is just generating, we can only say this is surjective. Now what you do is very simple. If you call this map phi, so phi inverse A tor, so let us come to phi inverse A tor, that will be a subgroup. So this is of course a finitely generated, this is a free abelian group of rank n, right. So being a subgroup that this will be also be free abelian group, right, and it will be in fact a finitely generated free abelian group. So this is finitely generated, so let us say generated by y1 up to yr. So this is what we obtained from what we have earlier proved, that any subgroup of a finite free abelian group of a finite rank will be of course free abelian group of finite rank. So if this is this by this, then this implies that A is generated by, sorry, A tor is generated by this phi y1 phi yr. Okay, that is quite clear. That is quite clear. So therefore A tor becomes, so given a finitely generated free abelian group A tor is finitely generated. This argument shows that, and hence by our earlier observation a finitely generated free torsion group is finite. So therefore we get this is finite, and furthermore I will quickly go through the things one by one, and furthermore then this, let me put it in this way, then A tor is finite. The second thing is A modulo A tor is torsion free. That is clear because all the torsion elements have now been moda has now been killed once we mod out by A tor, and hence A modulo A tor is free. It is free. It is free. The third thing that we want to talk about is, so now before making the third observation, try to see from A to A tor we have this projection homomorphism which is a surjective homomorphism, and this is free. So by means of with the help of a previous proposition we can say that there exists F, a subgroup of A, such that F is isomorphic to A, like, okay, let me put it in this way, such that A is equals to F plus A tor, okay, F plus A tor, such that and F is isomorphic to the F is isomorphic to A modulo A tor. Okay. In particular, F is free. Thus, we have seen that if you are given a finitely generated abelian group, then this can be decomposed like this. So, one part we will have this is called the torsion part of A, and this is called the free part of A. Of course, this decomposition is also unique in the sense that, so that is also a very obvious observation, that suppose A is isomorphic to like this, that it is isomorphic to some F prime and A prime, where F prime is free and A prime is a torsion. A prime is a torsion group. Then of course, then we will have a isomorphism between these two. This. So, by an isomorphism, elements of finite order, they go to elements of finite order and vice versa. So, this isomorphism will send A tor to A prime. Now, you quotient, therefore, it allows you to that induces an isomorphism between quotient of this by A tor and quotient of this by A prime, and that will immediately give you F and F prime will be isomorphic. Okay. So, this decomposition is also unique by up to isomorphism, that is what we have seen. And this decomposition is unique. So, that means whenever I am writing F as a direct sum of a free abelian group and a torsion abelian group, then that free abelian group must be isomorphic to F and the torsion abelian group must be isomorphic to A tor. So, therefore, this decomposition is unique. Okay. So, once we prove this uniqueness, now it makes sense to say like these things since these are characterized uniquely after isomorphism, we call it the free part of A, and this is what we call it the torsion part of A. Okay. So, now what is the story? So, given a finitely generated free abelian group, so this is finitely generated free abelian group. So, therefore, A will be as A is isomorphic to A tor. So, this F is a free abelian group. Of course, it is a finitely generated free abelian group because F is isomorphic to A modulo A tor. So, finitely generated free abelian group. So, this is this F will be isomorphic to some Z r copies of Z, right, and the rest part is finite. The rest part is finite. So, by the structure theorem for finite abelian group, we can write it as follows. Let us say some P1 PA11, P1 A1 N1, P1 N1. Similarly, P1 A PK AK1. So, at P1 P2 Pk are the all the distinct prime divisors of A tor. Pk, Ak, Nk. Okay. That gives us the, so every finitely generated free abelian group must be isomorphic to this for some r, and for some primes p, primes pi's and positive integers aij. Okay. And so, try to again understand every finitely generated free abelian group is isomorphic to something like this, and there the uniqueness of R and this aij that follows from what I previously said, that the free part goes to free part and torsion part goes to torsion part. So, for free part rank is uniquely defined, and for the torsion part, so that follows from the uniqueness of structure theorem for finite abelian groups. So, reducing it to finite abelian groups, we prove the uniqueness of these elementary divisors for any element. So, we prove the uniqueness of this for A tor. Okay. So, so once the uniqueness is established, we call R to be the rank, free rank of A, and these are the elementary divisors of A. So, basically we have decomposed A into a torsion part and free part. then the rest is just one part is taken care of by some general thing, and the rest is structure theorem for finite abelian groups. Okay, and I will just take one more minute, and with that I will finish. There is another form of the structure theorem which is called the invariant factor form. So I will just simply put it as an exercise. So any finite, let A be a finitely generated abelian group. Then there exist remember that here it may so happen that the free part is trivial if the group is whole, if A star is full of A. So then there exists positive integers, non-negative integers R, and positive integer, let us say n1 up to nl, such that n1 divides n2 and so nl minus 1 divides nl, such that, so we have a sequence of positive integers, each is dividing the next one, such that A is isomorphic to z to the power r, z to the power nl z. Okay, and furthermore these are unique. R and ni's are unique. Okay. So this follow, and how to prove that, let me just explain by just a small example. So suppose my for finite abelian groups I am showing, you know how to, then you will see, you will see yourself, I am sure that you can do it for the general case. So suppose this is what my situation, z modulo z4 and z modulo 3z and z modulo, let us say 5z. So this is my finite abelian group. So for this there is no free part. So how to put this in this form? So we write down the elementary divisors. For 2, 4, for 3 we have 3, 3, and if we just again here add one more term, that's not also a problem. Z modulo 8z, 2, 4, 8, let's say 3, 3, then 5. So first we take the product of the top powers. So 24 into 5, 120. So this will give you, so this z modulo 8z, z modulo 3z, z modulo 5z, that will give you z modulo 120z. Then once this has been crossed out, 4 into 3, 12z, and finally z modulo 2z. So by example, I showed that how to bring such an abelian group in this form, and so this example in fact shows you what should be the method for doing that. Corresponding to every prime, you first pick the top the top orders, and then take their product, form the cyclic factor, then cross whatever have been considered, and then go for the next top orders. So that's how you can bring it in this form, and free part is there, and their uniqueness also follows exactly in the same way. So given if A is isomorphic to two sums of this form, then from this you break each of these ni's and come to this so-called elementary divisor form, and from the uniqueness of the elementary divisor form you can prove the uniqueness of this n1 up to nl. So I leave the details to you as an exercise. Yeah, so with that I finish this lecture, and thereby this course is also finished. Thank you.